A beverage company has 2 bottling plants in different parts of the world. To ensure uniformity in their product, the variances of the weights of the bottles at the 2 plants should be the same. But Malachi, the company's vice president of quality assurance, suspects that the variance at bottling plant A is less than the variance at bottling plant B. To test his suspicions, Malachi samples 28 bottles from bottling plant A and 20 bottles from bottling plant B with the following results in ounces. So here is our sample from bottling plant A. Here is the sample from bottling plant B. Perform a hypothesis test using a 6% level of significance to test Malachi's suspicions. So we want to conduct a hypothesis test. In step 1 of a hypothesis test, we need to state the null and alternative hypotheses. So let's take a look at the problem and see what the problem says we want to test here. Okay, so here we'll go to Malachi's suspicions. Malachi suspects that the variance at bottling plant A is less than the variance at bottling plant B. So let's translate that into math. Okay, so variance at bottling plant A, so that's just the standard deviation at bottling plant A squared. That's the variance at bottling plant A. Malachi suspects this is less than the variance at bottling plant B. So that's the standard deviation of bottling plant B squared. This uses a less than symbol, so this would have to be our alternative hypothesis, which means our null hypothesis is just the same thing but with the opposite inequality symbol. So instead of a less than, we're going to use a greater than symbol. Greater than or equal to symbol, rather. Okay? So these are our hypotheses. But in order to test these hypotheses, we know we're going to want to use an F distribution. So instead of looking at these distinctly, looking at whether the variance at bottling plant A is less than the variance at bottling plant B, we want to look at the ratio, because the F distribution considers the ratio of the variances, right? So what I'm going to do is I'm going to divide both sides of each inequality by the variance of bottling plant B. Okay? And just rewrite my hypotheses in a more useful form. So the null hypothesis, if I divide the variance from bottling plant B, I get the variance from bottling plant A still, but then I am dividing by the variance of bottling plant B. Okay? Inequality symbol stays the same, but on the right-hand side, since I divided it away, the variance from bottling plant B divided by itself is just 1. Okay? And then I get something similar for the alternative hypothesis. Divide both sides by the variance from bottling plant B. I have the variance from bottling plant A divided by the variance from bottling plant B on the left side. And that's less than, and then I end up with 1 on the right side. Okay? These hypotheses are going to be the more useful hypotheses. Now, just to be clear, these are equivalent statements. They mean exactly the same thing. But this one is going to be a little bit more useful to work with. Okay, so that's the one that I want to pay attention to. And that's the one that the problem is asking about. Okay, so our null hypothesis is that sigma A squared over sigma B squared is going to be greater than or equal to 1. And our alternative hypothesis is sigma A squared divided by sigma B squared is less than 1. Because we are using a less than symbol in the alternative hypothesis, that means we are going to be performing a left-tailed test. We are interested in, we're going to be checking if there's more values in the left tail. What's the probability in the left tail? The probability that this would be less than 1. Okay? All right, so step 1 is all done. Step 2, now we need to assume the null hypothesis is true and identify the sampling distribution. Well, we already know that when we are conducting a hypothesis test, comparing the variances of 2 different populations, we are going to need an F distribution. The features of the F distribution are determined by the numerator degrees of freedom. In this case, we're notating that as dF sub A. and the denominator degrees of freedom, which we're notating as df sub b. So the numerator degrees of freedom, that's just the degrees of freedom corresponding to our first sample. So if we look at our first sample here, our first sample has 28 bottles from bottling plant A. So from sample A, we have 28 bottles. Our degrees of freedom is one less than that. So our degrees of freedom is 27. And from bottling plant B, our degrees of freedom from bottling plant B, well, we have a sample of 20 bottles from bottling plant B. And so our degrees of freedom corresponding to that sample is one less than that. So 20 minus 1 is 19. And so that's our degrees of freedom in the denominator that corresponds to the sample we are interested, the population we are interested in our denominator. Okay. We have step 2 done. We're on to step 3, find the p-value. And this is a little bit involved. We need to find the f-score. That's what we need to do to be able to plug in to this probability and calculate that probability. Let me move this over just a little bit so we have room. There we go. We want to find the f-score. To calculate the f-score, we're going to need the sample standard deviation from the sample taken from population A and the sample standard deviation from the sample taken from population B. Calculating a sample standard deviation we know is a little bit involved, so we're first going to calculate the sample mean from both samples, then calculate the sample standard deviation, then use those to calculate the f-score. And then we could use the f-score to find the probability and the p-value. Okay? Okay, so let's work on sample A first. Sample taken from bottling plant A. So I'm going to call this data x sub A, just so I don't confuse it with the data from my other sample. And as I've done in other videos, I'm using underscore to indicate a subscript. That's pretty common, and obviously I can't actually write a little a down there, so I'm using underscore A to indicate x sub A. Okay, and now let's find the sample mean and then the sample standard deviation. So x bar A, I'm just going to add up all my values in that in sample A, and then divide by how many there are. And I haven't actually got that yet, huh? So let me get that first. So the number of values in sample A is just length of x sub A. And so now I could divide by n sub A. Okay? So the average of that first sample from bottling plant A, is 14.98571. Okay? Now let's use that to find the sample standard deviation from bottling plant A. So S sub A, I need to use that sub A so I don't confuse it when I calculate my mean and my standard deviation from my other sample. I want to make sure I keep them separate. So I'm going to take each data value from the sample, subtract the mean, I square it, so I don't have to worry about the sign information. Then I kind of average it up. So I'm going to add them all up. But since it's a sample standard deviation, I divide by 1 less than the sample size. So n sub A minus 1. And then I take the square root of all that. So it's the same formula we've always used, but we do have to be a little bit careful that we use the data, the mean, the number of the sample size from the sample we're interested in, right? Which in this case is sample A. So I have that underscore A in the back of each one of these. Okay, and that's going to give me my sample standard deviation for the sample drawn from population A. And that's 0.6299408. Okay, now I'm going to do the same thing with sample B. I'm going to move a little faster this time. So grab all the data from sample B, put in a list, count how many there are, and then get the mean. So I'm just going to add up all the data and divide by how many there are. So the mean for sample B is 14.805. Notice the means are very close to each other, right? We're not testing the means, though. We're testing the standard deviation. So that's take the data value, subtract from the mean, see how far they are apart, square it, so I get rid of the sign information, add them all up, divide by 1 less than the sample size, and then take the square root of all that. And that gives me my sample standard deviation from sample B. Okay. Whew. Got my sample standard deviation from sample A, sample B. I'm ready to use those together to calculate my F-score. The F-score is going to be the ratio of the variances. So I'm going to have to make sure I square those sample standard deviations. Okay? So my F-score is the sample standard deviation from sample A squared to get my variance, divided by the sample standard deviation from sample B squared. And it is my F-score for this particular problem is 0.66666681. Okay, so now I want to use that to find the p-value. So I want to calculate the probability of this F distribution. And which symbol am I going to use? Well, remember, by the alternative hypothesis, I have a less than symbol. I'm doing a left-tailed test. And so I want to use a less than symbol here too. So I want to find the probability that if I grabbed 2 other samples, assuming the null hypothesis is true, if I grab 2 other samples, what's the probability that the F-score from those samples is less than the F-score from that I actually got? Okay, so now let's calculate this probability. So I want to calculate the probability of an F distribution. The quantile value is the F-score that I calculated. That is 0.66666681. And then I specify my numerator degrees of freedom, which is 1 less than the sample size from sample A, and my denominator degrees of freedom, which is 1 less than the sample size from sample B. Okay. You could also, we've already calculated these, so you could also just plug in 27 and 19 directly, if you prefer. Okay. And I am calculating the probability to the left in the lower tail, right? Because I'm using that less than or equal to symbol. So if I kind of drew this out, I have some kind of F distribution going on here. Maybe it looks something like that. Let's see if I can draw that a little better. Okay, that'll do. And 0.66666681, I don't know, let's say that's over here somewhere. Okay, and I want the probability that a randomly chosen F value would be less than that, so left tail. By default, that's what this calculates, right? This calculates the probability of the F distribution to the left of this value. So I don't have to do anything fancy. If I were to be calculating the probability in the right tail, I'd need to do 1 minus. But I'm not. I'm calculating the probability in the left tail. That's what this calculates for me already. I don't have to make any changes. And the probability I get is 0.1636288. And that is my p-value. Okay. Now let's draw a conclusion. And I'll just fill this up so we don't have those slider bars. We have the p-value equals 0.1636. We need to compare that to our level of significance alpha. So let's go back to the top. What was that level of significance again? We want to perform a hypothesis test using a 6% level of significance. So my alpha is 6%, or 0.06 is a decimal. In this case, the p-value is greater than or equal to alpha. When the p-value is greater than or equal to alpha, we do not reject the null hypothesis. We do not have enough evidence to accept the alternative. Okay? And so let's interpret that conclusion in words. We are deciding whether we can or cannot conclude that the variance of bottling plant A is less than the variance of bottling plant B. That's using less than, so that's talking about the alternative hypothesis. And if we can't reject the null hypothesis, then we cannot accept the alternative. So we cannot conclude that the variance of bottling plant A is less than the variance of bottling plant B.